Choose the name of one quadrilateral from the box that best. So let us just look on this quickly. This is the reflective symmetry. So normally when we just say symmetry, we're referring to reflective symmetry. We could see here that a kite has 1. The rhombus has 2. The square of 1, 2, 3, 4. The rectangle has 2. And these are just regular lines of symmetry. That's what we call reflective line of symmetry. A trapezoid, though, normally would have none, but there is a one-off case when we have, like, if I should let this side be the same as this side here in terms of the same length, then definitely if this is the same as this, I would have what is called an isosceles trapezoid, where if I put a line here, then the corresponding points would overlap if I should fold it along that line. So the thing is, a trapezoid doesn't normally would have symmetry except for this one. So there is a little case now where we can say, well, it has one. As it relates to rotational symmetry, the concept of that is, if you should pick a point, for example, if I should pick a point, say here, and I'm trying to rotate this, how many times while rotating it, I will end up getting back this exact shape before I reach 360. You understand? So if that is what we're looking for when we're talking about rotational symmetry. All right, rotating this and see how many times it would occur. You'll get back this shape while going to 360. All right, so let us go through now quickly to see how best we can respond to the questions. All right, so as you can see, the word best is very important here in our thing. So a dash has no lines of symmetry and has rotational symmetry of order 1. I would say here, I'll put the trapezium here. I'll put the trapezium here right now, because normally it really has no lines of symmetry, normally. All right, but there is a one-off case where we could find it, but ordinarily speaking, it has no line of symmetry. And if we should spin this around, I guess the rotational with order 1 would be based on the fact that when I go back to 360, because I don't think I'll be able to get that shape while just going around, right? All right, so the trapezium best fit there. Exactly 2 lines of symmetry and 4 right angles. This is not a square, because a square would have 4. All right, so what we're dealing with here is a rectangle with 2 lines of symmetry. So if I should just sketch my rectangle right there, we would have a line of symmetry going here. That's 1. We have a line of symmetry coming here. That's 2. So 2 lines of symmetry, and 4 right angle would be that rectangle, right? Now, let's go up some more. Now, this one, now, a dash has 1 line of symmetry, but no rotational symmetry. This is kind of funny. So the word best, in this case, a kite, because it cannot be a square has 4 lines of symmetry. A rectangle has 2, a rhombus has 2, so definitely the kite would be the best fit from the 5 that we're taking from, basically. So the kite is the best fit. The diagram below shows 4 straight lines, right? 4 straight lines. We're looking at 2 parallel lines. You could see the arrows here denoting parallelism right there, right? So those lines will be denoting parallelism, right? All right, let's see what the question really is dealing with. We're asked to find the value of P of Q and R. All right, finding the value of Q and R. So this is vertically opposite here. This is 54 degrees right there. All right, that's 54 degrees right there. And from this, we're seeing where if this is 54, and these are parallel lines cut by a transversal, then angle Q plus angle R the value would give us 180, and that is based on the co-interior, right? So these angles are co-interior. So basically, angle Q is simply 180 minus the 54. And remember though that I brought in that angle there for vertically opposite angles, because vertically opposite angles are equal. So I just brought that in there. So this would become my 126 degrees right now. So we have 126 degrees, and that's for the Q. All right, which are the angle that they asked there? So Q is 126 degrees. R, as you can see, R is 54. Vertically opposite angles are equal. So right here, when we have two straight lines, anytime we have like two straight lines, this angle here is vertically opposite to this, and this one here is vertically opposite to that. So they share the same value. So the question reads, give a reason why angle P is equal to 71. So angle P, this is 71. They are alternate. So alternate angles, when we have alternate angles, they are equal when we're dealing with parallel lines, right? So angle P is alternate to 71, and it's what we call the Z angle sort of thing. So that Z angle is equal. So we have that sort of thing going on. This angle here is equal to that. It's alternate angles are equal when we're dealing with parallel lines. Below shows triangles X prime, Y prime, Z prime, and X double prime, Y double prime, Z prime prime, drawn on a square grid, and we're seeing those here right now. Let's see what the question is. The question says triangle X prime, Y prime, Z prime is the image. It is the image of triangle X, Y, Z after enlargement of scale factor 2 with the center 5, 1. All right, so after an enlargement. All right, so what I did was, all right, let us just look at it right here. At this, all right, so this would have been my X, and this is my Y, and this is my Z, right? And these are primes, all right? Now, what we're saying is that when we have an enlargement, so we were told that there is an object. So this is an image that we have here. This is an image, right, that we have. That's an image. So this is saying to us that there was an object somehow that was actually half this size, because what happened was the scale factor K was 2. So if the scale factor was 2, that means this image that we're seeing here was actually 2 times as large as the object. So where would the object be? All right, definitely the object would be between the center and the image. It's going to be halfway between that, because one of the rules surrounding the enlargement is that from the center, the distance of the points from the center, they share a very unique relationship. So for example, this is where the center is. To this point Y, if I want to know where the original object was, then all I have to do is to measure this and take half of it, and I'll get the point Y, half of this distance. All right, that's one thing. There's another thing that we could do. One of the things that we could do is to count from the center. Watch this. If I count from the center, I'm getting 1, 2, 3, 4, 5, 6, 7, 8, and then I go up 1, 2. So there, if I go 8 and then 2 up, if I take half of that journey, which means I'm going to go 4 and 1 up, I will land at the corresponding point for Y. Watch. All right, let's go for it. So we're going for this. So let's go 1, 2, 3, 4, and 1 up right there. It's going to give me my Y. So that's the point I'm making, that there are a number of ways you could get there. But what we're saying is the center of the enlargement, there is always a straight line through the center, through the corresponding points. So you could work with the lines, all right? And so in this case, all I need to do is to find those half distance all the way, and I'll get back the object. That's one. Another thing that I could do is to simply, the moment I find 1, I could start working my idea, because if this side is 4, obviously, if I divide it by 2, I'm expecting the other side to be 2 that corresponds with it. So if I know the point y that links to y prime here, and I see that this is 4, I could just count 2 go up, just like that, 1, 2, and I'll get the next point here. And this that is 2, it's going to be 1, and you could see that 1. We're saying, okay, so this is my object right here. So firstly, you want to connect lines from the center through the image that you have, and then you could manipulate that line to find back the object from the beginning. So we're looking at this. Let me just clear it up. So we're looking at the fact that this is the object. And remember, we could not have manipulated the coordinates by dividing by 2 to go back to the object, because we were not at 0, 0. So the center was somewhere else from 0, 0. We could employ counting, or we could use the distance of the image from the center and use that to create the relationship to find the object. All right. So I hope you did that. All right. All right. So we just drew that. The next question says, triangle x prime, y prime, z prime is mapped onto triangle x double prime, y double prime, z double prime by a reflection in the line P. State the equation of the mirror line P. So we were already told that there was a reflection in the line P, but what we know about reflection is that from the mirror line, corresponding points are equal in distances from the mirror. So you'd have to look at this and create a halfway between. All right, so it's up to you. You want to do it. Some people would pick on this y here and pick on this y here, and then you could say, all right, let's just look. It's a 1, 2, 3, 4, 5, 6 jump. If it is a 6 jump, then halfway between that is a 3. So this would be my mirror P, halfway between. All right. Now, what is the equation of this? As you could see, passes through 2. So it is where x is equal to 2. So my mirror line is x equal 2. And then you would have just simply collect that mark easily. X is equal to 2.